Okay.
So, hello everyone, good morning and welcome back to the second week of our summer school. It is with great pleasure that I want to welcome Professor Harald Pfeiffer, who is here with us today from Germany. Professor Pfeiffer is a group leader of the Astrophysical and Cosmological Relativity Division at the Max Planck Institute for Gravitational Physics in Potsdam. He's very well known in the numerical relativity community, having championed the first pseudospectral methods to construct initial data for astrophysically realistic binary black hole systems. And he's also one of the founding developers of the spectral Einstein code that has been hugely successful in modeling and studying in detail the various gravitational wave events that we have seen so far over the past few years and so on. And on a different note, he's had a long-term relationship with ICTS. He was also one of the inaugural lecturers at our first summer school in this series 10 years ago. So it's with great pleasure that we welcome him back again here. And now I'll give the mic back to him to start discussing PDEs and how to solve them.
Okay, thank you. Yeah, I actually wasn't aware that this was the first summer school 10 years ago, but it's a really pleasure being back here. I enjoy my visit. I have had very good interaction so far. And I'm looking forward to talking more to all of you during the coming week. So this course is a little bit a change of topic to last week in that it is more broad and more basic. So the topics I'm talking about are solutions of partial differential equations with spectral methods. So spectral methods are one of the primary tools you can use when you're trying to solve partial differential equations. Other ones are finite differences and finite element methods. But for this week, we're focusing on this one set of tools. And it wasn't really planned from Geoffrey's and my sides, but the split has worked out that I'm doing the basics. I'm really explaining the little details. And the goal is for you to develop, in my part of the course, your very own little tools and little library of codes to solve partial differential equations without using any other routines. So you really understand what's going on and how simple this actually can be if you do it right. Geoffrey then, the second lecture of this week, is going to introduce the Spectre code and showing you all the extra difficulties you have to go through if you want to turn these really neat, simple ideas into production quality science. Okay, so what type of equations are we talking about? And I'm actually quite open to pretty much any type of PDE. And so our goal is to solve equations like the Laplace equation, so elliptic equations. And such elliptic equations you probably already have seen all over your physics career, but they also appear, for instance, when you're computing initial data for general relativity. And I understand Professor Baumgartner talked about this last week, how you actually begin setting up an evolution of black holes. Another important type of problems are hyperbolic problems. So most important, the wave equation with a function of space and time, and you have the second time derivative of that function, for instance, in the simplest possible case, equal the second spatial derivative of the function. So that's the prototypical hyperbolic equation. It's a wave equation, and it's used to evolve things from one time into the future. So typical examples are wave equations or the evolution part of general relativity. The third class of problems that also fits quite nicely into the spectral methods scheme are eigenvalue problems, where you have equations like u double prime of x equals an eigenvalue times the function u itself. And so, such eigenvalue problems, for instance, occur when you do look for modes of oscillating strings or quasi-normal modes of black holes. Quasi-normal modes. Okay, so all these very diverse types of equations can be done with spectral methods. And so let me next give you the top-level view of what spectral methods actually are. The fundamental idea of spectral methods is to expand in basis functions. So let me start. And you expand the solution, of course. And basis functions could be pretty much many different things. It could be a Fourier series. It could be Chebyshev polynomials. And there's a few other choices as well. I will focus on Fourier and Chebyshev. Professor Lovelace will then also switch over and use Legendre polynomials. So let me start with a simple intro example of how this can look like. I should say two things at this point. Number one, I know my handwriting is quite bad. If you can't read anything, please speak up and ask about it. I have this habit of having my handwriting deteriorate more and more until somebody complains. And so if somebody asks me to write nicer, I will do so. If not, you will, unfortunately, I fear, suffer more and more. The second thing is we also have a few different languages here. I'm a German native speaker. And so if you don't understand my pronunciation, again, please interrupt and ask. And perhaps even more important than the logistics of making sure you understand what I'm saying, if you have any questions about anything at any time, please also just raise your hand and ask. The whole exercise here becomes a lot more fun, a lot more engaging, and a lot more useful if we actually have more of a dialogue than me just talking here and you just listening. Okay, so our first example is a nice little ODE, elliptic ODE, second space derivative of a function x minus x to the 6 plus 3x squared times the function itself equals 0. We have x in -1 to 1. And we have boundary conditions. -1, u is supposed to be 1. And at +1, u is supposed to be 1. In these types of introductory examples, it happens very, very frequently that ones appear all over the place, like interval ±1, boundary conditions 1, coefficients 1. It's just the simplest example you can do. And putting in more constants doesn't really change the gist of what's going on. So that's the thing you want to solve, a nice little elliptic equation. And in our spirit of expanding in basis functions, we're taking our solution u of x, and we are approximating it by a function un of x. And I'm using, hopefully fairly consistently, the subscript upper n for a numerical solution, which is only going to approximate the actual true solution. Because anytime you do numerics, you have to cut down from an infinite number of degrees of freedom in an arbitrary function to a finite number of degrees of freedom that your computer can handle. And so, in this simple example, I'll start in a slightly unusual way. Namely, well, I'll start with a Taylor series with a0 plus a1x plus a2x squared. I'm modifying it to immediately incorporate the boundary conditions, the u at plus minus 1 equals 1. So I'm putting a 1 minus x squared in front of this thing here. So I'm starting out with a fourth degree polynomial, originally five unknowns, but because I'm already imposing the boundary conditions, I'm only having 3 unknowns left. And so once you write down this type of expansion in basis functions, there's immediately a bunch of very important consequences. And those are some of the very reason that makes spectral methods so useful and interesting. So the first thing is, I can evaluate my approximation for any x. So fundamentally, there aren't any grid points in spectral methods because everything is based around full functions that are living everywhere on the computational domain one is interested in. Curiously enough, grid points will come back in a little while because it turns out you can do spectral methods remarkably well with grid points. But, so not just at grid points. So, and this differs, for instance, from finite difference methods, where you're starting with just data at grid points. And whenever you want the data between grid points, you have to do something special. You have to interpolate. Here, it's all there. Yeah.
I quite follow what you said. After grid points would come back.
Yeah. Yes.
But for what you said?
We'll get to that. That's at least half of today's lecture. Getting back to grid points and explaining why they're useful at the end of the day after all. But conceptually and fundamentally, we always deal with functions, not with discrete data. The next cool thing is, because we have functions and we know all about the functions, so here I'm picking a very simple Taylor series, but even if we have Fourier series or Chebyshev polynomials, we always have known basis functions where we can compute the derivatives as well. And so we can always compute derivatives exactly. So we can take our function here and we can compute dun dx. And well, it is something. And this one I even can do by hand. It's a minus 2x, a0 plus a1x plus a2x squared plus 1 minus x squared a1 plus 2 a2x. So you can do this. You can also compute second derivatives and you can go so forth. And then you can also, so these are the two really important things. And then you can also compute the residual. Exactly. So the residual is substituting in the approximate solution into our original equation. So that's, how far down into this corner can I go while you can still see what I'm doing? One more line, or is it?
No, I'm just blocking there.
So no, okay. Then we have to switch over to the left-hand side here again, but no problem. So the residual is obtained by substituting our approximate solution into the original equation. So it will be something like x. So this whole thing is a function of x. And now comes the fun part. Because un is not a true solution, only an approximately one, therefore our residual will not be identically zero, but only in some strange, weird sense to be decided on, approximately zero. So and what we don't have yet, and which is the next step, is that we now need to figure out how to determine our coefficients here. Once we have these coefficients, then we have our approximate solution and the problem is solved. And so that's the basic steps to do when doing those spectral methods. So to solve, we need to find those three numbers. And to do so, we need to have three equations that we can solve for these three numbers. And one obvious and simple thing to do is that our residual should vanish so let's simply try to set it to zero exactly at three different values for x. So at plus minus 1, the residual is going to vanish simply because of how I had chosen my basis functions here. And so, well, I'm picking three x values between plus 1 and minus 1, minus 1/2, 0, and 1/2. And I'm actually requiring that the residual to identically vanish at these 3 points. Right now, I'm just picking these points. Later on, I'm going to explain you how to pick them correctly. But this is the intro example. Everything is as simple as it can be, just to get a flavor of what's going on. Okay, so the UN and the UN double prime all are linear in the A0, A1, A2. There's never a square of those things around. And so there's some algebra involved doing the second derivative. But if you go through this algebra, what you end up at the end of the day is that out comes three equations, three linear equations for A0, A1, A2. And those three linear equations we can solve. And once we have solved them, we put them back into phi n. And then we are done. We have our approximate solution. Okay, let's try and do this on the computer. Do we have any questions at this point?
Yeah, so when you propose the approximate solution, how do you put it into translate the, or like how many coefficients do you use? Like you have chosen 3, right?
Okay, so I've chosen 3 here because this is about as much as I can handle by hand without doing things systematically. And in principle, what we will do later is we will choose smarter basis functions because a Taylor series is really, really bad. And then we will go up to some arbitrary order n. And by the choice of n, we can then choose how accurate our solution is going to be. If we pick a small n, the amount of work is very little, like here on the blackboard right now, but the solution is only modestly accurate. If you pick a high end, you have somewhat more work, but you get a much more accurate solution out of it.
I have the same question.
Okay.
Because there are 3 coefficients.
Exactly.
So if there are say any number of coefficients, it may so in that case we have to look at n different points. So how these points can we choose suitably? Because can you choose any point?
This is a very, very good and very important question. So just to repeat, I had 3 coefficients, therefore I have written down 3 equations. Yes, if we now go up to n coefficients, because we have n basis functions, then we need n equations. And at that point, you have to pick n different values here if you want to keep to this scheme that I'm sketching out here. And it actually turns out that the choice of how you choose these points is extremely important. If you do it right, this whole spectrum method really, really shines. If you do it wrong, the whole spectrum method system becomes really, really bad. And we'll get into all of this as we go longer through the course. Okay, let's see whether I can get Zoom back. Did I drop out of the meeting?
So you could also choose the answers like u and x equals a0 plus a1 and x squared and impose that u minus 1 is 1, u1 is 1.
You guys are great. You're asking all the right questions about all the topics I will get to later. Yes, this question was about boundary conditions. This method I'm choosing here to do boundary conditions is not very flexible. It works as long as the boundary conditions are simple enough that you can really impose them by manually this way. But in general, we will not do this anymore after this example. And we will rather make a very general expansion here without regard to boundary conditions, and then figure out how to put the boundary conditions here into the solving for the coefficient part. Simply because it's more flexible.
You can just share screen.
Yes.
Okay, got it.
Yeah, okay. Share screen.
This is the first one.
Yes, okay, wait a second. I first need to find where my thing is I want to share. Let's move this over here. Yeah, share screen. Okay, here we go. Okay, so let's
make it full screen.
Let's do the things we've just talked about. In Python. I'm using Python here, and I'm also having the tutorials for you based around Python. My understanding is most of you know Python. If you prefer a different language, by all means, nothing is Python specific. But it's a really nice language for introductory things. And if you really get into high-end production coding, of course, you will switch away from Python for the compute kernels, but all of that I leave to Geoffrey to talk about. I'm doing the simple things here. Okay, a Python notebook. I need a little bit of SymPy because I'm too lazy to do the derivatives by hand. And now here's the SymPy. What is this little bulb? I have no idea. So here I'm defining my function un. And I'm using SymPy to compute its second derivative. It's not really that hard differentiating a fourth order polynomial, but it's easier this way. And then I can also still SymPy compute the residual as a function of x. So I'm taking the second derivative minus this term over here. And out comes the residual, which is at first still a function of my free variable x. And it also contains, of course, still the A0, A1, A2 coefficients, because we haven't removed them yet. So we have this modestly long function here in the middle of the screen. And now we want to compute the residual at x equals plus minus 0.5 and at 0. And outcome, as promised, 3 linear equations where the coefficients simply are whatever these complicated x expressions are evaluated at 3 different values of x. So we get 3 equations, and as promised, it's at this stage a linear system of equations for the 3 coefficients. And solving it gives you, wherever it is, a solution of minus 0.2050 and minus 0.205. Those numbers are actually certain. In this particular example, those are actual rational numbers, 500 something or else divided by 2,575, something like that. But it doesn't really matter whether it's a rational number or a floating point number or anything. Okay, and so if we now substitute this back into our original function, we have our solution. And that's what I'm doing here, because I'm not really a big SymPy expert. I've just figured out how to get my 3 numbers back in as floats in Python outside of SymPy. Then I'm picking a linear grid between here -1 and 1, and I'm evaluating again anew the approximate solution on this grid. So this is now NumPy, no longer SymPy, so just good old numbers and good old arrays. And as it happens, the exact solution for this problem is this one here, e to the x to the 4th minus 1 divided by 4. In fact, the way many of these types of examples are arrived at is you first pick your solution. What was it? You first pick your solution, and then you differentiate and put it here, the u double prime, and whatever you get when you're differentiating the second solution, you're putting here to make the equation work out. But that's not here and not there. This is just an example anywhere. But as it happens, we know the exact solution. And then let's plot these stuff. So we have, again, the coefficients, but this time as floating point numbers and not as SymPy things. And then what comes out of this are here plots. The left-hand side, the blue line is our approximate solution. The orange line is the exact solution. And here's the difference. They agree with each other to about plus minus 0.01. So given that we only used 3 degrees of freedom, and this whole calculation is remarkably short, I think actually this is quite an impressive outcome.
Shouldn't the residual go to 0 at 0.50 and 1?
Excellent question. So the question is, shouldn't this thing here be 0 at our plus minus 0.5 and 0? So this is the difference between the function un and the exact solution u. What we've set to 0 is this combination of u, the full differential equation. So those two things are different. And again, thank you for your question. What I'm doing next is I'm taking the residual and I'm actually plotting the residual as a function of x. So this is now this function over here, which is the one we were setting to 0. And if you now look at this plot, it indeed is 0 at minus 0.5, at 0, and at plus 0.5. And as advertised already, it is non-zero elsewhere. Usually it is small, as it is supposed to be, because that's what we're hoping for. But in this particular example, it's actually getting quite large towards the edges. And this is this is a factor caused by two different things. Number one is that right at the edges, we weren't imposing our differential equations anymore, but instead we were using the boundary condition. And so the boundary condition is of course also important, but since we're not using this thing at the boundary, we can't really expect this thing to be small at the boundary, and well, it isn't. The second feature that comes in here, and this is perhaps already a portent of not using Taylor series, is if you're using Taylor series, they tend to work very well in the interior, but towards the edges, and especially past the edges, they blow up very violently and very rapidly. And this might already be foreshadowing here with this type of behavior. Okay.
So if instead we chose some points fixed at 0, but near the edges, closer to edges, then would we have a better solution in terms of residuals more close to 0?
You know, I have no idea. This is a very good question. And of course, it's one thing you could do, say turn the minus 0.5 into minus 0.7, and by moving the 0 here further to the right, distributing your errors more uniformly. Let's see what happens. I honestly have no idea. The whole thing is simple enough that I can just play around here. Okay. So now let me play the following game. Print F previous solution. Since I'm overriding my data, I will print out the previous solution plus minus 0.7. And this one here was plus minus 0.5. So we can get a sense of whether numbers actually have changed and by how much. So the coefficients definitely have changed. The 0.25 turned into the 0.205 turned into 0.225. Now let's see. This one I'll just do anew because I don't want to overwrite these. I should have done everything anew. So here's the solution with 0.7. And as you can see, it works a lot better. The left side visibly is better. The right side is no longer plus minus 0.016, but plus minus 0.006. And let's also plot the residual again. That one now goes down to minus 1.2. And beforehand, it went down to minus 1.6. So it's somewhat improved. And yes, we could now play around more, moving the points around more by hand. But the difficulty is this moving of points and comparing to how big the errors are works in this particular case very well because we know what the solution is. In reality, the better way forward is to stay to the standard points, which I'll tell you what they are, and then increase resolution, and that way make it more accurate.
Are you choosing these points symmetrically because the ODE itself is?
I was choosing the points symmetrically simply because the interval is symmetric around 0. And so, because the interval, if you go from A to B in an interval, it makes sense that the left side and the right-hand side is mirrored of each other. And yes, in this particular case, it also makes sense because the problem is axisymmetric and the solution is axisymmetric. And if you probably have noticed that A1, that coefficient has been 0 throughout, well, because it breaks axisymmetry. I could have anticipated this and left this term out, but usually it's just too much effort anticipating such things. One just puts everything in, and if some of the terms are 0, well, no big harm. Okay, let's switch back and move over to doing things more systematically and more in depth. We'll start with the case that's perhaps most familiar to you, and that is Fourier series. It's more familiar, and it turns out it's the simplest case because of a lot of the concepts that show up. The formulas are just a little bit simpler than elsewhere. So perhaps I should have said all of this before I'm erasing the blackboard, but we now have already come up with a few of the very important questions we need to address in the rest of this lecture and in the coming days. One of the questions was what boundary conditions to use, and I've already told you Taylor series isn't good, but what else to use and why? Another one of the questions is how do you do the boundary conditions? A third question was, with these conditions here to impose the residual to be 0 at certain grid points, how do you choose these points most suitably? So and all of these questions is the topic of the near future now. Okay, let's get started and let's talk about Fourier series. So typically a Fourier series of a real function, or of a function, you can write as, if you prefer the sine cosine expansion, it would be a constant, and then it would be many cosines of different frequencies, and then it would be many sines of different frequencies. Sine nx. So if I'm putting integers here, this means I'm going to use x as an interval from 0 to 2 pi. And Fourier series are periodic by construction, so they will work best for periodic data, or they will work for periodic data. And of course, you can also write this Fourier series as in terms of complex numbers. So you have C0 plus you have a sum n going from minus infinity to plus infinity, n not zero because I took out the 0, 1 of 1/2 Cn twickle e to the I n x. And both are fully equivalent to each other because we have e to the ix equals cosine x plus I sine x. And if you use this identity here, if you replace your exponential by sines and cosines, or vice versa, if you replace the cosines and sines by exponentials, it's not hard to work out that the coefficients are related by Cn equals an minus ibn for positive n's, and C minus n, Cn equals okay, so there must be a typo in my notes somewhere. Oh no, C minus n is an plus ibn. Yes, there's a typo in my notes. So you get the negative n's and the positive n's in the complex series from the a's and the b's above. And finally, if u is real, then in the sine cosine expansion, all the a's and b's must be real. Then from these relations over here, we have that C minus n equals Cn complex conjugate. And then we can write the complex expansion as C0 plus some n equals 1 to infinity, 1/2 Cn e to the I nx plus
From now on.
From now on, okay. I just want to fit the text in here, that's why I became smaller. Plus C n twickle star e to the minus I nx. So I'm combining the plus n and the minus n together. For the minus n for the coefficient, I already put in the complex conjugate. If you also complex conjugate the exponent here, the minus turns into a plus and you have the same as over here. And then this whole thing becomes a real part. And this turns out to be the real part of the sum n equals 0 to infinity, C n trickle e to the I nx. And because I wanted this nice end result here without any 1/2s floating around for real functions, this is why I started out over here with the unusual 1/2. Okay, so this is how you can express a Fourier series both in sines and cosines, how you can express it in terms of complex exponentials. Don't forget the real part if you're expanding a real function. And here's the condition how the complex coefficients and the sine and cosine coefficients are related to each other. So we have at least all our variables sorted out. I was making sure to put all this up here because in the tutorial, I'm actually asking you to code all the things I'm going through here right now. Okay, the next step here is, say we have our favorite function u of x. How do we get at the coefficients? And so, given u of x, compute the coefficients probably have seen this before. The trick to do here is that you're integrating your function against the e to the minus INX. And this works because of orthogonality. Let me write this below. That if you take two different ones of our basis functions, say e to the ikx and e to the minus inx, and you integrate this from 0 to 2 pi dx, then this is equal to 2 pi delta kn. If your two oscillating functions have a different number of periods, well then over the full 2 pi, they're going to average out the positive and the negative parts. If the two things are totally in phase, you get e to the ikx times e to the minus ikx. Well, everything cancels away, you just get 1, and integrating 1 over 2 pi gives you the 2 pi. And it's this thing here where you take your series, you multiply by e to the minus ikx, you integrate, and then the orthogonality makes the coefficient pop out because the coefficients turn in the basis functions turn into delta functions. So that's the way how you do this in Fourier series. And now comes an important calculation that will point us towards why this whole approach here, expansion in basis functions, and especially Fourier series right now for periodic functions, are so immensely powerful. So let's see. Namely, we are talking about the behavior of our coefficients for large n. Let's start again with this equation here. And I'm putting the 2 pi on the left-hand side, simply to have a little bit less to write on the right-hand side. So we have u of x times e to the minus inx dx. And I'm going to happily integrate by parts here. And I'm always getting this wrong, so I'm really happy having my notes here. The important thing you need is e to the minus inx dx is I over n e to the inx minus. And so if we integrate by part, we get this thing times u, e to the minus inx, I over n, from 0 to 2 pi. And we get the derivative on the other side. We get a u prime of x times e to the minus inx dx. And I have the I over n sitting here in front. Okay, now let's look at the boundary term. E to the minus I 2 pi n is 1 and e to the 0 is 1. So this thing here is u of 2 pi minus u of 0. And that is 0 if u is periodic. So we've gotten rid of this thing here. We're only having left the second term. And now we're going to integrate by parts again. And what we find this time around is a minus I over n, u prime of x e to the minus I n x from 0 to 2 pi, plus minus I over n squared integral from 0 to 2 pi, u double prime of x e to the minus I n x dx. Again, looking at the boundary terms here, the exponential is again 1 at both ends. And so this term here becomes u prime of 0 minus u prime of 2 pi. And that is going to be 0 if u prime is periodic. And if we do this in total k times, we still end up with a boundary term which is going to be 0 if periodic. And then, watch here. Each integration by part brings out a factor minus I over n from this term over here. Minus I over n squared. So down here, I now have a minus I over n to the k times the integral 0 to 2 pi, the kth derivative of x e to the minus I kx dx. Okay, so that's the calculation. And now let's consider what this tells us about the coefficients themselves. So if U is periodic, and C infinity and C infinity, then we can play this game arbitrarily often. And so we have that our Cn is going to be order 1 over n to the k for all k. And so the Cn's decay faster than any power of n. And that's called exponential convergence. And that means that our coefficients very, very quickly become very, very small, which means if we go on, that keeping only a few of the basis functions that I have removed, we will be able to get astonishing accuracy of our solutions. So that's the nice case. But what else can happen? If UK is not periodic, then we would have Cn goes like 1 over n to the k plus 1, because We have this term then left over. And if U1 is not periodic, we have a 1 over n squared sitting here in front. So this is k plus 1. And finally, if U is only element of Ck, so it's k times continuously differentiable, then the integration by parts breaks down. And we find Cn is going like n to the minus k plus 2. And so the storyline here is that if the functions we are looking at are smooth and periodic, we are in a very good case, very good shape. If not, well, then not. So what are the categories we have here? So if U is smooth and periodic, I'm a numerical relativist, numerical physicist. I'm not a mathematician. I'm using sometimes symbols that I only vaguely define. For instance, here I'm saying smooth, here I'm saying C infinity. I actually don't know whether mathematically those two things are completely equivalent or identical. They are close enough for my purposes here. So if we are smooth and periodic, then Cn exponential decay. And the truncated Fourier series so Un is the sum n equals 0 to n over 2 Cn tilde e to the minus inx is very accurate. And so this is the use case. This is the case we want to be in. If U is non-smooth, well, then the Cn's decay slowly. Slow decay of Cn requires many terms. So that where you don't want to do. So this isn't a good case to be in, but perhaps even worse, you run into something that's called Gibbs phenomenon. And that gives you errors of order 1, independent of how many terms you keep. So you can crank up the number of terms in your Fourier series. If you have a non-periodic function, discontinuous function, near the discontinuity, the Fourier series will always overshoot. And the amount of overshoot is not going down as you are increasing n. The range, how far away from the discontinuity it overshoots, that one becomes smaller and smaller, but the overall peak error remains large. I'm sure Kenta has talked about this last week, because where this is leading to is precisely the shock capturing techniques you should be using here, and you shouldn't use spectral methods. So no spectral the right tool for the job. If you have non-smooth problems, well, spectral methods aren't the tool you should be using. And the Gibbs phenomenon is on the first tutorial among other explorations of everything I'm talking about here. Yes?
How about smooth in your domain but not in your domain?
You guys are great. And I have managed again to have a very awful planning of my Blackboard space. Smooth and non-periodic. So you don't use Fourier series, but you use Chebyshev or Legendre polynomials. And we'll do this later, either today or tomorrow, depending on how quickly I make progress here.
So the Fourier basis is as inefficient as in the case of the non-smooth function. In this case also, if we use the Fourier series, it is as inefficient as in the case of non-smooth.
Exactly. So if you have a non-periodic function like this one here, and you're trying to use it, so this looks great. And if you're now trying to Fourier transform it, what the Fourier transform is going to do, it will mold this into a sine and cosine expansion. And so it will implicitly take this one here and keep on expanding it. And so what the Fourier series actually sees would be this sawtooth pattern, which has glaring discontinuities. And just because you happen to have put them right at the edge of your interval, doesn't make them go away in terms of the Fourier series. Okay, so all of this is grand and swell. But now we need to get down and work out how we can actually do this in practice on computers. That means at some point we now need to get away from our infinite series and exact integrals and actually turn into a finite number of terms, because otherwise we can't do this on computers. I guess I'll start here on the left-hand side and work my way again to the right. So, Fourier series in practice. The first point I need to remind you of, or tell you about, is Gaussian quadrature. So, Gaussian quadrature is a way of evaluating integrals very precisely. So, you have a function f of x that you are given, and you happen to want to be able to integrate integrals of the form of f of x times a weight function rho of x dx. So the weight function might just be 1, or for instance, it could be 1 over 1 minus x squared, or pretty much anything else which shows up in your application. So what Gaussian quadrature does is it approximates this integral as a sum over n points, where you're evaluating your function at suitable x values, and you're weighting each point suitable with a suitable weight. And this would be Gaussian quadrature of order n. By the way, I'm trying throughout this course to keep the capital symbol N to be identical to the number of grid points, like here the xj, that's why I'm going from 0 to n minus 1. But also for the Fourier series, it turns out I put the n over 2 here, because as we'll see in a little while, the Fourier series up to n over 2 works on precisely n grid points. And so I'm trying to keep the n constant for the number of grid points. I'm also always starting counting at 0, simply because both of these put the formulas I'm putting on the blackboard into most easy to translate into Python code, because you always are going to talk about arrays of length n that have indices from 0 to n minus 1. Many spectral papers and spectral codes have a different convention that they go up to n. They either start at 1 and go up to n, or they start at 0 and go up to n. And all of this looks great as long as you're just writing equations on a paper, and it's actually easier than always writing the n minus 1. But once you then now start coding this, you suddenly deal with arrays that start at 1 or that go to n plus 1, but all your muscle memory is programmed to have arrays in Python from 0 to n minus 1. And if you're breaking this muscle memory, the likelihood of making an accidental indexing mistake increases by a very large magnitude. That's why I personally switch to always have n the number of grid points. Which means that some of the formulas I'm putting on the blackboard will look slightly different by plus minus 1 from what you're finding in Boyd or in other references. Okay, so
how do we define the weight function? Is it already predefined, or is there any constraints?
the weight function is predefined, and it basically comes from the problem at hand. It turns out for Fourier series, the weight function is going to be 1. It turns out for Chebyshev polynomials, the weight function is the 1 over 1 minus square root of x squared. And it's a detail that is floating around, but it actually has very little impact on what's going on. Okay, so now that the beauty is, we have, when you now want to determine the w's and the x's, we have 2n unknowns here. And so we can use these 2n unknowns to make this formula as good as it can be. So, and specifically, what was shown by Gauss and others is that for given rho, there exists weights and collocation points, grid points, such that this formula up here is such that star is exact for polynomials with degree is exact for f of x polynomial with degree less than or equal to n minus 1. So you can, if you take say a 6th order quadrature, you can put in here a 13th degree polynomial, and this formula will work exactly. So it's an astonishingly high order polynomial accordings you can get here. And what this means is that for sufficiently smooth, smooth f of x, the Gaussian integral is astonishingly accurate. This, by the way, harks back to two different things. You need the smooth f because otherwise you won't have the high order polynomial expansion, and therefore this argument doesn't hold water. And here now shows up already foreshadowing how we are going to choose grid points later on. It's going to be related to the grid points that come out of Gaussian quadrature formulas. Okay, let's play this game for our Fourier series. For periodic functions, there's a similar thing around as Gaussian quadrature. And I will only be using n even, otherwise I'm running into so many if n even, if n odd distinctions. I don't want to go there. Choice is to use your grid, you distribute your grid points evenly on your intervals 0 to 2 pi. And the W's are also just constants, 1 over n. And now what you find is that the equivalent of the Gaussian quadrature for periodic intervals is not that the formula I'm writing down is good for polynomials, but it is going to be good for trigonometric polynomials, for sines and cosines and exponentials. And this is precisely what we want, because we wanted to have our coefficient, if I'm writing down the formula once again, u of x e to the minus akx dx. I should be careful to use the same index left and right. Kx, k over here. The idea is now to approximate this by 1 over 2 pi n and a sum over u of xj e to the minus I k xj. J is going from 0 to n minus 1 over all our grid points. And if I'm also introducing one more piece of nomenclature here, I'm going to write uj as u of xj. So this is the value of the function u at the jth grid point. Then I can keep on writing here 1 over 2 pi n. Sum j equals 0 to n minus 1 uj e to the minus I. Up there is my formula for xj, 2 pi kj over n. And on the left-hand side, I have c trickle k. So at that point, I want to make two remarks. The first remark is, what I did from here to there is good old trapezoidal rule. Of integration, or perhaps even just square rule. I don't really know the names to. And this typically has an error that goes like your delta x to the second power. But it turns out, if your function u is smooth and periodic, then, as we have seen, its spectral coefficients are decaying off astonishingly quickly. And for periodic functions, this one happens to be a Gaussian quadrature, which is exact for remarkably high sine and cosine Fourier terms. And so it actually turns out that this lowly trapezoidal rule for smooth and periodic functions is astonishingly accurate. We're going to do this trapezoidal rule with 10 points, and we're getting 10 to the minus 8 or 10 to the minus 10 accuracy out of it. You'll see this in the tutorials later. The second important point to make is that this formula here is a real valued fast Fourier transform. So going from the grid point values, here they are, to the spectral coefficients can be done with a fast Fourier transform. And conversely, and what this fast Fourier transform is going to do us, it will take the grid point values uj and the RFFT will turn it into the spectral coefficients. So the 0th one is a real number. C1 to Cn over 2 minus 1 are complex numbers. And Cn over 2 is again a real number. And if I've counted all my indices correctly, that means we have n numbers over here on the left-hand side, which are transformed into n numbers here on the right-hand side. And the C0 and the Cn over 2 are real only because for those two things, the sign terms vanishes. The sign of 0 times x is 0, so we don't have to carry around a coefficient for x. The sign over here, sign of n over 2, x is of course not 0, but the sign n over 2 at our collocation points is a sign pi n j, yes. J is 2 pi, xj is 2 pi j over n, the 2 cancels. Sine pi n j, that happens to be exactly the zeros of the sign.
Do you use a yellow or white?
Yes, I can. Okay, so we have going from real space values to the spectral coefficients is a fast Fourier transform, and you won't be surprised to now learn that going the opposite way is going to be an inverse fast Fourier transform. So back to real space, well, we have uj is the real part of the sum Cn trickle e to the I n xj. And if I'm putting in my xj, this is going to be the real part of Cn trickle e to the I 2 pi j n over n. And this is just the inverse real FFT. So you can go back and forth by doing FFTs from C trickled and an IFFT gets you to UJ. How am I doing in time? How am I doing in time? 10 minutes? Okay. Okay. Now the next thing we want to do is, and the final thing we are going to do today, is we begin taking derivatives. I'm sorry, I didn't catch this. Could you repeat? Which 2 pi? Sorry, over here. So here is not yet a 2 pi because this is an xj. And
before the summation. No, not like before the summation. That.
Yes.
So since your limit is from 0 to 2 pi and you have a factor of 1.
I'm sorry, I'm completely lost what the question is about.
I'm saying the expression is correct because it should be, I expect it should be 1 by x instead of 0 from 0 to minus n, and it should not be 1 by 2 pi.
Because the integral is from 0 to 2 pi. Summation, the normalization of 1 over 2 pi goes away.
No, it doesn't. Because what we are doing is, let's just integrate from 0 to 2 pi at the function 1. And yes, you're probably right. You're probably right that somewhere here could be 2 pi errors. I will not try to find them here on the blackboard.
The quadrature rates to be just 2 pi by instead of 1 by.
It could very well be that it's that simple. Let's put them in. But they're actually not changing anything of the argument. Okay, derivatives. The IKX, and we want to take a derivative. So what we get is the IK comes down, CK sum over K, CK, e to the IKX. And if you look carefully, this is exactly the same series expansion we started out with. So I'm going to write this as the real part of the sum CK tilde e to the IKX, where the CK tilde prime is IK CK tilde. So the coefficient here gets modified, but we get again back a series in the very same basis functions we had. And therefore, what we can do at this point is to take derivatives. You start at the real space values to an FFT, getting CK, multiply by IK and call this CK delta, CK prime. And now you do an inverse FFT of CK prime, and that gives you UJ prime, which is UN dx at the grid points. So what now taking derivatives boils down to is you do three very simple things and you're done. Okay, to close this, I have a second demo of just how well this can work. So let me get back to my computer. And let me find the second demo. Yep, so I have a fairly big standard header where I'm just getting Python to be nice. The file Fourier contains a bunch of the results that things routines I'm using here. And so let's start with the function e to the minus cosine x. I have a 10-point grid here, and I'm plotting e to the cosine x, e minus cosine x, and I'm plotting the first derivative. And these are the analytic solutions, and they look only so coarse because I'm using merely 10 points to do them. So if I now begin playing Fourier games, I already have coded for myself one of the functions I'm asking you to do in the tutorials this afternoon, namely that does this step here to compute the spectral coefficients. And so here's a plot of the absolute values of these spectral coefficients. And the first one is 2.5, but even the third one on a linear scale, you can't even distinguish from 0 anymore. So I have to switch over to a log scale here to make this more visible. And now if I'm finding the right plot again, what's wrong? I have no idea what happened now. Here we go. You see that we're still starting at 2.5 with the 0th coefficient, but by the time we get even to the 3rd or 4th coefficient, we're already at a factor of 1,000 smaller than originally. And this is just this illustration of how amazingly quickly these spectral coefficients can decay if one does everything right, and if the function and the problem is suitable for these tools. Okay, here's the calculation of the derivatives. This little function du dx Fourier is also one I'm asking you to code. And it does precisely these three lines here. Compute spectral coefficients, multiply by IK, and go back to real space values, and that's it. And out of here comes a plot that has my approximate calculation, and it has the exact derivative, because I'm starting with a simple function. I just can take the analytic derivative. Here's the plot of both. You can't see a difference. And here's a plot of the difference. And the difference is 0.0004. of a function that's of order 1. So we have about 4 significant digits, despite playing all these games with only 10 grid points. Okay, so you ask, hopefully you ask, because you should be asking, what happens if you change n, the number of grid points? And so once you begin changing n, this type of calculation gets, the type of Python snippets gets a little bit more complicated. Here's a loop over different n's. I'm setting up a grid with n points, and I'm computing every time anew my 2 analytic functions, as well as I'm playing the Fourier spectral game of computing the derivative with Fourier spectral methods. And all the rest of here is plotting. The left-hand side are the spectral derivatives computed this way. And they're all quite close to the result. The biggest deviation from the result that you're actually seeing here is that Python connects the individual points with straight lines. And so the blue curve here isn't bad because it's away from the true answer, but the blue curve only appears so bad here because, well, Python puts a straight line here, discarding all the cool high accuracy power of the Fourier series in the background. So to see how good this actually is, the right panel plots the differences between the exact solution, the exact derivative, and our spectral calculation of the derivative. And with 8 points, well, you're up at just above 10 to the minus 3. With 16 points, you're at 10 to the minus 7. With 24 points, you're at 10 to the minus 12. With 32 points, the whole calculation saturates at around 10 to the minus 15, because this is approximately the accuracy with which computers represent floating point numbers. And it's when Fourier methods work, or spectral methods, they can work remarkably well. And I think at that point I'm out of time. So your tutorial for today is to actually code these types of functions that can make you use Fourier spectral methods, and then to explore this example and a few others to get a feeling of how quickly the series are converging and how you can compute derivatives. And then tomorrow we'll go on and ask and address the question that Ajith asked: what do you do for non-periodic problems? Okay, thank you very much.
Understand why increasing the values of capital N in that plot, right plot. So why the nature is destroyed, like kind of the errors, like for higher N, for N equals to 32, it's kind of random, right? The errors. Do you understand why is that?
Yes. So this truncation here at around 10 to the minus 15, this is called a numerical round-off error. So computers represent numbers only to a precision of about 10 to the minus 16. And so more accurate numbers simply cannot be represented because the usual floating point numbers only have 8 bytes. And this is not a 10 to the minus 16, but more than 10 to the minus 15, because there's a lot of calculations going on. And so small errors of order 10 to the minus 16 accumulate and give you slightly larger errors there. And so this is a typical feature, that whenever you're trying to do calculations too accurately, at some point you're running into this floor of not being able to do better. If you do Mathematica or other symbolic languages, you can increase the number of significant digits, but we'll just stop here and call this good enough. Okay, thank you. Coffee time.